Have you ever thought about what the world is truly made of? We see solid chairs, liquid water, and the air we breathe. It all seems so normal, so predictable. If you kick a ball, you know where it will go. If you drop a rock, it falls. This is the world of classical physics, the rules that govern our everyday lives. These are the rules Sir Isaac Newton figured out centuries ago. They work perfectly for things we can see and touch. But what happens when you zoom in, way in? What happens when you look at the fundamental building blocks of everything around you? That's where things get strange. Very strange. Down at the level of atoms and the particles inside them, the comfortable rules of our world break down completely. This is the realm of quantum mechanics. It's a place where particles can be in many places at once. Imagine a single electron existing here and there and everywhere in between, all at the same time. This is called superposition. It's not just a guess, it's a reality of the quantum world. Particles can also be connected in a spooky way, no matter how far apart they are. What happens to one instantly affects the other. Einstein famously called this spooky action at a distance. It's a world that defies our common sense. For centuries, biologists have explained life through chemistry. They saw it as a complex dance of molecules, a series of chemical reactions governed by classical laws. Think of it like a giant, intricate factory. You have raw materials coming in, assembly lines of enzymes putting things together, and finished products going out. This mechanical view has been incredibly successful. It helped us understand DNA, cure diseases, and unravel many of life's mysteries. But it might not be the whole story. There are some puzzles in biology that classical chemistry struggles to explain completely. Some processes just seem too perfect, too efficient to be purely random chemical reactions. Consider a plant. It takes sunlight, water, and carbon dioxide and turns them into energy. This process is called photosynthesis. It is the foundation of nearly all life on Earth. But how does it do it so well? When a photon of light hits a leaf, its energy needs to be transported to a reaction center where it can be converted into chemical energy. The journey is through a dense, crowded forest of molecules. Classical physics would suggest the energy just bounces around randomly, losing a lot of its power along the way. But photosynthesis is nearly 100% efficient. How? It's as if the energy knows the exact perfect path to take every single time. This is where quantum mechanics enters the picture. If life on Earth has learned to use these quantum tricks, it completely changes how we should think about life elsewhere in the universe. Our search for extraterrestrial life has mostly been a search for life as we know it. We look for planets with liquid water, a comfortable temperature, and the chemical building blocks we see on Earth. We are essentially looking for another Earth. But what if life doesn't need such cozy conditions? What if quantum mechanics provides a toolkit for life to survive and thrive in places we once considered completely uninhabitable? This is the exciting frontier where quantum biology meets astrobiology. Imagine a planet orbiting a dim red dwarf star. It receives very little light. For life to exist there, photosynthesis would need to be extraordinarily efficient, capturing every single photon it can. Perhaps life on such a world would have evolved even more advanced quantum light harvesting systems than the plants on Earth. Quantum effects could be the key to survival in low-energy environments. Or think about a world blasted by cosmic radiation. Could life use quantum effects, like quantum tunneling, to repair its DNA faster and more accurately than the radiation can damage it? It's a fascinating possibility. Life might not just be adapting to its environment. It might be using fundamental physics to cheat death. Let's start with one of the most famous and mind-bending ideas in quantum mechanics, superposition. Imagine you have a coin. In our everyday world, if you flip it, it will land as either heads or tails. It has to be one or the other. You can check. But in the quantum world, things are not so definite. A tiny particle like an electron can be like a spinning coin that never lands. It isn't heads or tails, it's both at the same time. This state of existing in multiple states at once is called superposition. It's not that we don't know which state it's in. The particle is literally in all possible states simultaneously. It only chooses one definite state, like heads or tails, when we try to measure it or look at it. This concept is so strange that it's hard to wrap our heads around. Think of it like a light switch. A normal switch is either on or off. A quantum switch can be on, off, and everything in between all at once. It's a haze of possibilities. The moment you try to check if the light is on, the switch instantly decides and becomes either on or off. The act of observation forces reality to pick a side. This idea was famously illustrated with a thought experiment called Schrödinger's cat, where a cat in a box is linked to a quantum particle. Because the particle is in a superposition, the cat is considered both alive and dead at the same time, until you open the box to check. Why does this matter? Because this isn't just a quirky thought experiment. Superposition is a real feature of the universe that we exploit every day. The powerful computers we use are built on transistors, which are essentially tiny switches that are either on or off, representing a 1 or a 0. Now let's get even weirder. The next quantum concept we need to understand is called entanglement. Albert Einstein famously called it spooky action at a distance, and for good reason. Imagine you have two quantum coins, and you entangle them. This means their fates are now linked, no matter how far apart they are. If you flip them and send one to the other side of the planet and keep the other with you, the moment you look at your coin and see its heads, you will instantly know that the other coin, thousands of miles away, is tails. Every single time. It's as if they are communicating faster than the speed of light, which should be impossible. This connection is instantaneous and unbreakable. It doesn't matter if the second coin is in the next room or in another galaxy. Measuring one particle immediately influences the state of the other. It's not that they were secretly set up as heads and tails from the beginning. Before you looked, both coins were in a superposition, a mix of both heads and tails. But their combined fate was sealed. If one is heads, the other must be tails. It's a perfect correlation that defies our classical understanding of space and separation. Two particles, once entangled, act as a single system, even when separated by vast distances. They share a single, unified quantum state. This isn't just a theory. It's been proven in countless experiments. So if this strange connection is real, could life have found a way to use it? This is one of the most exciting questions in quantum biology. Some scientists have proposed that entanglement could play a role in how a bird navigates. Our final quantum trick is a bit like being a ghost. It's called quantum tunneling. In our everyday world, if you throw a tennis ball at a solid wall, it will bounce back. It doesn't have enough energy to break through the wall. The wall is a barrier. This seems obvious. You can't just walk through a solid wall, no matter how hard you try. The rules of classical physics are very clear on this. You need to have more energy than the barrier's strength to pass through it. If you don't, you are stuck on one side. This is true for tennis balls, people, and planets. But for quantum particles, the rules are different. An electron can do something impossible. It can appear on the other side of a barrier without ever breaking through it. This is quantum tunneling. A quantum particle, like an electron, also behaves like a wave. This wave doesn't just stop at the barrier. A tiny part of its probability wave can leak through. This means there is a small, but non-zero chance that the particle will simply teleport from one side of the barrier to the other. It doesn't smash through the wall or find a hole. It just vanishes from one side and reappears on the other, as if the wall wasn't even there. The thicker the wall, the lower the probability, but it's never zero. It's like being a ghost and just passing through a solid object, a feat that is impossible in our large-scale world. This ghostly behavior is not just a theoretical curiosity. Quantum tunneling is essential for some of the most fundamental processes in the universe. The sun, for example, would not shine without it. The core of the sun is hot, but not hot enough for two protons to overcome their mutual repulsion and fuse together according to classical physics. Let's look at one of the most important processes on our planet, photosynthesis. It's how plants eat sunlight. This single process is the foundation for almost all life. It takes the energy from a photon of light and converts it into chemical energy, the fuel that powers a plant's growth. For decades, we thought we understood it well enough. A photon hits a chlorophyll molecule in a leaf, exciting an electron. This energy then hops from one molecule to the next, like a bucket of water being passed down a line of firefighters, until it reaches a special place called the reaction center. There, the energy is locked in as stable chemical fuel. It's a simple, classical picture. But there was always a problem with this story. It was too slow and too wasteful. If the energy was just randomly bouncing from molecule to molecule, a lot of it would be lost as heat along the way. The journey through the dense forest of molecules inside a cell should be chaotic and inefficient. But when scientists measured it, they found something astonishing. Photosynthesis is nearly perfect. Almost 100% of the light energy that is absorbed makes it to the reaction center. How can it be so good? How does the energy avoid getting lost? It seems to know the single most direct and fastest route through the molecular maze every single time. This level of perfection baffled scientists for years. It was as if the plant had a perfect GPS guiding the energy packet home. The answer, many scientists now believe, is quantum. Specifically, the quantum trick of superposition. Remember, in the quantum world, a particle can be in many places at once. The idea here is that the energy, in the form of an exciton, doesn't just try one path. Now let's move from plants to animals. Consider the European robin. This small bird is a master navigator. Every year it migrates thousands of kilometers between Europe and Africa, often returning to the very same garden it left months before. How does it do it? It doesn't have a map or a compass in the way we do. For a long time, scientists have suspected it uses the Earth's magnetic field to find its way. But the Earth's magnetic field is incredibly weak, about 100 times weaker than a refrigerator magnet. How could a tiny biological system in a bird's brain possibly detect such a faint signal and use it to navigate across a continent? The answer might be one of the spookiest ideas in physics: quantum entanglement. The leading theory is called the radical pair mechanism. It sounds complicated, but the idea is fascinating. It starts when a photon of light hits a specific molecule, called cryptochrome, in the bird's retina. This jolt of energy creates a pair of electrons that are quantumly entangled. Their fates are linked. These two electrons have a property called spin, which you can think of as a tiny internal magnet. Normally, their spins are linked in a specific way. But the Earth's magnetic field, as weak as it is, can influence these spins. It can change the relationship between the entangled electrons, pushing them into a different state. This change happens depending on the angle of the magnetic field relative to the bird's head. This is where it gets really clever. The chemical properties of the radical pair molecule depend on the spin state of its entangled electrons. In one state, the molecule might produce one chemical signal. In the other state, it produces a different one. We have seen quantum effects in how plants get energy and how birds navigate. What about a sense we have right here on our own faces? Our sense of smell. How do you distinguish the smell of coffee from the smell of roses? The traditional explanation is called the lock and key theory. It suggests that molecules of different shapes fit into specific receptors in our nose, like a key fitting into a lock. A coffee-shaped molecule fits into a coffee receptor, and a rose-shaped molecule fits into a rose receptor. This triggers a signal to our brain, and we perceive the smell. This model works for many smells, but it has some serious problems. There are molecules that have the exact same shape but smell completely different. For example, take the molecules vanillin, which smells like vanilla, and isovanillin. They are made of the exact same atoms and have very similar shapes, but isovanillin smells nothing like vanilla. The lock and key model struggles to explain this. This puzzle led some scientists to propose a radical new idea: the vibration theory of olfaction. This theory suggests that our smell receptors don't just detect the shape of a molecule, they detect how the molecule vibrates. Every molecule is made of atoms connected by chemical bonds, and these bonds can vibrate like tiny guitar strings, each at a specific frequency. What if our nose is designed to hear these molecular songs? But how could a biological receptor hear these vibrations? This is where our final quantum trick, quantum tunneling, comes in. The theory proposes that when a smell molecule lands in a receptor, an electron on one side of the receptor wants to move to the other side. However, there is an energy barrier in its way. When we think about searching for life beyond Earth, we usually look for planets like our own. We search for the Goldilocks zone, where a planet is not too hot and not too cold, but just right for liquid water to exist on its surface. This makes sense. Water is essential for all life as we know it. But the universe is a vast and violent place. Most planets are not like Earth. They face conditions that would seem like a death sentence for terrestrial life. They might be frozen ice worlds, planets blasted by deadly radiation, or worlds orbiting dim stars that offer only a whisper of light. Classical biology tells us that life in these places would be impossible, but what if life had a secret weapon? What if quantum mechanics provides a toolkit for survival in these extreme environments? This is where the story gets really exciting. The quantum tricks we are just beginning to uncover on Earth, superposition, entanglement, and tunneling, might be the key to life's resilience across the cosmos. These effects aren't just about making things more efficient. They could be the difference between life and death. They could allow organisms to perform feats that seem to defy the harsh rules of their environment. Maybe the Goldilocks zone is much wider than we thought, if life can use quantum physics to its advantage. Consider a planet with a very thin atmosphere or no atmosphere at all. It would be relentlessly bombarded by high-energy cosmic rays from its star and from deep space. This radiation shreds complex molecules like DNA, breaking them apart and making life, as we understand it, unsustainable. On Earth, our magnetic field and thick atmosphere protect us from the worst of this. On Earth, our sun provides an abundance of bright, powerful light. Plants have evolved to capture this energy through photosynthesis, a process we now suspect is enhanced by quantum mechanics. But, most stars in our galaxy are not like our sun. They are red dwarfs. These stars are much smaller, dimmer, and cooler. A planet orbiting a red dwarf would be a gloomy twilight world, bathed in low-energy reddish light. For life to survive there, it would need a photosynthetic system that is far more efficient than anything we see on Earth. It would have to be a master at capturing every single precious photon that reaches its surface. This is a perfect scenario for quantum effects to become a matter of life and death. On Earth, the quantum coherence in photosynthesis makes the process nearly 100% efficient. On a dark world orbiting a red dwarf, life might have evolved even more sophisticated quantum systems. Imagine, if you will, alien plants or microbes whose light-harvesting molecules are held in a perfect, rigid structure to maintain quantum superposition for even longer. This would allow the energy from a single, weak photon to spread out over a much larger area, guaranteeing it finds its way to a reaction center without getting lost. Their survival would depend on being the ultimate quantum machines. What would this life look like? Plants on Earth are green because chlorophyll is very good at absorbing red and blue light, but it reflects green light, which is less useful. On a red dwarf planet, the light is mostly red. To absorb as much of it as possible, plants might be black or a very deep purple. One of the greatest threats to life in space is radiation. Outside the protective bubble of Earth's atmosphere and magnetic field, cosmic rays and stellar flares can wreak havoc on biological molecules. The most vulnerable target is DNA, the instruction manual for life. A single high-energy particle can shatter its delicate double helix, causing mutations that can lead to cancer or cell death. Any life form that wants to survive on the surface of Mars, or on a moon like Europa, would need an incredibly robust way to protect and repair its genetic code. Classical chemistry offers some solutions, but they can be slow and imperfect. This is where quantum tunneling could play a superstar role. DNA repair is a chemical process. It involves enzymes that find the damaged section, cut it out, and replace it with a new correct piece. Many of these steps involve moving atoms, particularly hydrogen atoms, which are just single protons, from one place to another. This often requires overcoming an energy barrier. According to classical physics, the atom needs a big push to get over the barrier. But, quantum tunneling allows a proton to simply pass through the barrier as if it were a ghost. This would make the repair process happen millions or even billions of times faster. Imagine an organism living on Mars, where the thin atmosphere offers little protection from solar radiation. Its DNA is constantly being damaged. To survive, it would need a repair system that works almost instantaneously. Life on such a world might have evolved enzymes that are perfectly tuned to facilitate proton tunneling, making its DNA repair mechanisms hyper-efficient. It would be in a constant race, with quantum mechanics providing the speed needed to fix damage faster than the radiation can inflict it. If life on other worlds uses quantum mechanics to survive, how strange could it get? We've explored how quantum effects could enhance processes we already know, like photosynthesis and DNA repair. But what if an alien species evolved to use quantum phenomena in ways we can barely imagine? What if their biology is not just quantum-assisted, but fundamentally quantum in nature? This leads us to speculate about life forms that would be truly alien, operating on principles that challenge our very definition of a living organism. These possibilities might sound like science fiction, but they are logical extensions of the physics we know to be true. Consider quantum entanglement, the spooky action at a distance. Could a colonial organism, like a vast mat of microbes or a forest of interconnected fungi, use entanglement for communication? Imagine a network of cells spread over a large area. If they could link particles within themselves, an event happening to one cell, like finding a nutrient source, could instantly transmit information to the entire colony. There would be no need for slow chemical signals. The entire organism would act as one, a single coordinated entity connected by an invisible quantum web. This would be a powerful advantage for survival in an environment where resources are scarce and scattered. What about superposition? Could an organism exist in a superposition of states? This is much more speculative, as maintaining quantum coherence in a large, warm object is incredibly difficult. But perhaps a microscopic alien could use it for hunting or evasion. It could exist in a superposition of multiple locations at once, only collapsing into a single spot when it finds its prey or is detected by a predator. So, if life really is using quantum tricks, how do we prove it? It's one thing to have these incredible theories about quantum photosynthesis or bird navigation, but, it's another thing entirely to design an experiment that can actually catch these delicate effects in action. The biggest challenge is that the quantum world is just incredibly fragile. A state of superposition or entanglement can be destroyed by the tiniest disturbance. A stray vibration, a bit of heat, or even just the act of looking at it. This is why, honestly, most quantum experiments happen in highly controlled, isolated labs, often cooled to near absolute zero. A warm, wet, and messy living cell is the last place you would expect to find these effects. But scientists are getting clever. The first front in this search is right here on Earth, in laboratories around the world. Scientists are building incredibly sophisticated tools to probe the living world at the quantum level. One of the most important technologies is ultra-fast laser spectroscopy. These lasers can fire pulses of light that last for just a femtosecond, a millionth of a billionth of a second, and this is fast enough to take snapshots of energy moving through a photosynthetic molecule. It's like having a camera with an impossibly fast shutter speed. By using these lasers, researchers have been able to see the quantum beating, the wave-like sloshing of energy as it explores all paths at once, providing the first direct evidence for superposition in photosynthesis. Searching for quantum life in the lab is one thing. Searching for it across light years of empty space is a whole different level of challenge. We can't just go to an exoplanet and scoop up a sample. We have to rely on the faint light that travels from these distant worlds to our telescopes. For decades, astronomers have been analyzing this light to look for biosignatures, clues that life might be present. Usually this means looking for the chemical fingerprints of gases like oxygen or methane in a planet's atmosphere. But if we want to find quantum life, we need to look for something more subtle, something stranger. One of the most exciting tools we have for this is the James Webb Space Telescope, or JWST. With its incredible sensitivity, it can analyze the atmospheres of exoplanets in stunning detail. So what quantum clues could it find? Let's go back to the idea of photosynthesis on a dim red dwarf planet. To be super efficient, life there might have evolved pigments that absorb light in a very specific, unusual way. These so-called quantum pigments might leave a unique signature in the light that is reflected from the planet's surface. The JWST could potentially spot these strange absorption patterns, a clue that something very different from normal chemistry is at play. Another idea involves looking for something called chiral preference. Many biological molecules, like amino acids and sugars, can exist in two forms that are mirror images of each other, like your left and right hands. Life on Earth almost exclusively uses left-handed amino acids and right-handed sugars. No one knows why. One theory suggests that this preference could have been influenced by the quantum interactions of polarized light in the early solar system. If we could analyze the light reflected from an exoplanet and see a similar strong preference for one type of molecular handedness, It would be a powerful hint that life and perhaps quantum processes are at work. While telescopes look for clues from afar, other missions are being planned to get a closer look. To truly find evidence of quantum biology in our own solar system, we need to send probes that are equipped with the right tools. We can't just send a rover with a camera and a drill. We need to develop a new generation of instruments that can detect the subtle signatures of quantum mechanics in a sample of ice from Europa or soil from Mars. This means shrinking down the complex, room-sized equipment we use in labs on Earth and making it rugged enough to survive a journey through space. One promising technology is a miniaturized version of an electron paramagnetic resonance, or EPR, spectrometer. This is the kind of device scientists use to study the entangled electrons in the radical pair mechanism. Imagine a rover on Mars scooping up a soil sample. An onboard EPR machine could then zap the sample with microwaves in a magnetic field to see if any biological molecules within it show signs of long-lasting quantum entanglement. Finding such a signal would be a monumental discovery. It would be strong evidence for life that has adapted to the harsh radiation environment using quantum-level tricks. Another key mission would be to search for evidence of quantum tunneling in action. This could involve an instrument designed to measure the rates of chemical reactions in extreme cold. For example, a probe landing on Saturn's icy moon Enceladus could analyze the organic molecules found in the plumes of water erupting from its surface. If it finds that certain chemical reactions are happening much faster than classical chemistry would allow in those freezing temperatures, it would be a smoking gun for quantum tunneling. It would suggest that life could be thriving in a subsurface ocean, its metabolism powered by these ghostly quantum leaps. We stand at the edge of a profound shift in our understanding of life itself. For so long, we have viewed life as a magnificent, intricate clockwork machine, a collection of molecules and chemical reactions that ultimately followed the familiar classical rules of the world we see around us. But the discoveries of quantum biology are showing us that this picture is incomplete. Life is not just a classical machine. It is a quantum engineer. It has learned to reach down into the weird, counterintuitive world of subatomic particles and harness its power. It uses superposition to achieve impossible efficiency, entanglement to sense the world, and tunneling to make its chemistry run. This realization does not just change biology. It completely revolutionizes our search for life in the universe. We have been searching for life as we know it, looking for planets that mimic the cozy conditions of Earth. But quantum biology tells us that the rulebook for life might be far more flexible than we ever imagined. The ability to use quantum tricks could allow life to survive and even thrive in environments we have long considered dead and barren. A frozen world, a dimly lit planet, or a world blasted by radiation might not be a wasteland. It might be a habitat for an organism that has mastered quantum physics to overcome the odds. This is a paradigm shift for astrobiology. The implications are staggering. It means we need to broaden our search. We need to look beyond the Goldilocks zone and consider the vast number of planets that we once dismissed. We need to develop new tools and new methods, not just to find the chemical signs of life, but the physical signatures of quantum mechanics at work. So, where does this leave us? We are faced with a universe that suddenly seems even more mysterious and full of potential than before. The possibility of quantum life forces us to ask bigger and bolder questions. Is life a rare classical accident that happened on one lucky planet? Or is life a fundamental property of the cosmos, an emergent phenomenon that learns to use whatever physical laws are available to it, including the weirdest ones? Could it be that life is common, but we have simply been looking for it in the wrong way, with the wrong tools? These are the questions that will drive the next century of scientific exploration. The future of this field is thrilling because it is so unknown. It lies at the intersection of the two greatest scientific mysteries, the nature of life and the nature of quantum reality. As we build more powerful telescopes like the James Webb Space Telescope, we will be able to peer into the atmospheres of distant worlds with unprecedented clarity. As we develop more sophisticated probes and landers, we will be able to search for quantum signatures directly in the soil of Mars or the ice of Europa. We are on the verge of being able to test these incredible ideas. We are moving from what if to how can we find out. Ultimately, this quest changes us. It expands our perspective. To even consider the idea of a quantum alien, a creature that uses entanglement for communication or superposition for hunting, is to stretch our imagination to its limits. It reminds us that the universe is not obligated to conform to our common sense. The reality of nature is often stranger and more beautiful than we can conceive. The search for quantum life is a humbling exercise. It forces us to admit how little we truly know and to embrace the possibility that we are about to discover something that will change everything. The next great discovery may not come from finding a microbe that looks like one from Earth. It might come from detecting a strange energy signature, an impossible chemical reaction rate, or an unexplainable physical correlation on a world 100 light-years away. It might be a signal that we don't understand at first, a clue that life is not just playing a different chemical game, but a different physical one. The search continues, driven by the most powerful question of all: are we alone? And with the lens of quantum mechanics, we have a tantalizing new way to look for the answer.